All right, so welcome to the workshop on R once again. Sorry about that interruption. And this is the second workshop. We had the first workshop last week, Friday. That's the recording is on our YouTube channel if you missed that. And this workshop is a continuation of the last one. Once again, we welcome Lee DeCola. He's a course instructor at the University of Maryland, the Baltimore County, as well as a retired federal scientist. And this is going to be continuing from the last time. So if you missed the last workshop, it's on our YouTube channel. And if you have any comments, once again, you can reach out to Lee personally, or if you prefer CCing me as well in the mail, you can, of course, send a courtesy copy if you want, if you wish. And but generally, Lee's email is on the screen right here, just at the right side of his R Studio GUI, and so on. So, but welcome once again. We should just get started learning and hacking because that's really what I want to do right now. Yeah. So if you have any questions, you can place them in the chat, or you can unmute yourself if you're not in a very noisy area and ask Lee personally so that we can, learn from your questions and listen and all get the knowledge from today's workshop. So I'll be muting right now, and it's just going to be Lee from now on. Yeah.
Okay. Good afternoon, everyone. I think it's afternoon wherever you are. Oops, you can see you probably can't see my picture. You see the R Studio screen in front of us. So this time I'm running R Studio. Last time I ran R GUI. My cat is climbing over my computer at the moment, so she's a bit of a ham. And I'm going to have the chat window open on the left. So if you have questions, please don't hesitate to type in a question. I'll keep that on my screen. So running R GUI or running R Studio are pretty much the same. I pretty much organized the R GUI with the script on the left and the console on the right, and then the environment on the bottom. So I'm going to assume what I'd like you all to do is, if possible, run R, either R Studio or R Standalone, and follow along with me. It's very important that you can watch what I'm doing, but it's not as motivating as if you do it yourself. So this time, what we're going to do is open up a R script. So you go to File, New File, R script, and then we get a window on the upper left of the R Studio, and we can see that we have places for a script. And last week we filled up that space. Well, the last week we ran on the console window, but this time we're going to run a script. So the first thing I generally do is, if I'm writing a script, is I'll put a comment into the script line, and then I'm going to say on that script line, analysis of Nile data. I'm actually going to put in lowercase N-I-L-E data. And I use Nile in upper and lowercase because it's actually a data set. But so can anybody see that? Send me a chat if anybody is having trouble, or just send me a chat saying I can see your screen, I can see the text, or I can't see anything, or I can't see it easily. Let's hear from somebody. I can see everything. Okay. Adaibo Kyo said that they can see everything. Good. So if what I'm going to do today is download some data. So I'm going to create a object, lowercase nile, and I'm going to assign it the function or the results of the function read table, and I'm going to put in a return, and then I'm going to type in quote http colon / ldecola.net /files /nile.txt. I'll give you time to type that, and I'm going to hit. I'm going to execute that command, and if it works correctly, nothing should happen in the console window. So I do Control Enter, and I get the. Why is that? Oh, okay. Yeah. So in the control window, I get the fact that the command executed. So I'll give you all time to type out that URL. That's a URL, http://ldecola.net, which is my website. Within my website, there's a directory of files, and in that directory is a file called nile.txt. So I'm assuming you all have access. Obviously, you all have access to the internet. Well, maybe not. I don't know. I don't know how Google and all this stuff works, but I'm assuming you all have access to the internet, and therefore you're able to download that file from my website. And I executed that command. I typed Control Enter, and nothing happened, which was a good sign, because if it hadn't worked, there'd be an error message. So if I type in the letter Nile, the letters Nile now on the left, you can see that there's that in the environment on the bottom left of the RStudio window is a response that the object Nile exists. But if I type the command Nile in the script window and hit Control Enter, I get 100 numbers and 100 indices. So if I scroll up, I can see that those numbers are entered into the computer's memory. And if I just want to look at the first few numbers, which is more typical and a more conservative thing to do, I type in HEAD Nile and then Control Enter. I get the first 6 lines of that file. What I would like is that for those numbers to be a vector of numbers, but they're actually a data frame. So if I do class, type slowly, parenthesis, Nile, Control Enter, it says it's a data frame, and the dimensions of that data frame is 101. So it's a data frame that consists of 100 rows and 1 column. So I really don't want. I'm hearing voices on somebody getting a phone call from their girlfriend or something. So what I want is a vector of numbers. So what I'm going to do is create a time series, and if I go to Control TS, $TS, on the bottom right-hand screen, I get a help file. Oh, I got to type it. Actually, let's type it in let's type that in the command window. $TS. If I type in the command window, the console window, the command $TS, I get, I'm going to expand that. I get help for a command window. Now it looks like that's not visible very, I wonder if I can, I don't know how to make that bigger. I guess I should learn how to make that. That's a help. So if you want to know what the TS function is, it's a function that creates time series objects, and it really only requires one argument, the data, and the data has to be a vector or matrix. But if you want it to be a legitimate time series, you have to tell it at what time unit does the time series start. So what I'm going to do is create a object called Nile.ts, and I'm going to set it equal to time series object, and I'm going to then indent just to make things a little clearer. I'm going to set it to the first column of that data frame. And then I'm going to, now if we go back to the console window and I type in, oh, I'm not going to, let's see. Oh, let's forget it. Let's not do that. All right. So I'm going to just set it as the first object, and then I'm going to hit and control. And I've created the Nile. Now you can see on the bottom, the environment says that you have the object Nile, which is a data frame, and then the object Nile.ts, which is a time series. So if I type in class Nile.ts, I had 3 S's, it says that it's a time series. If I type in structure, it tells me that it's a time series with 100 observations that range from 1120. Well, it starts with 1120 and then 1160 and 963 and so forth. And if I do a summary of Nile.ts, it gives me a minimum of 456 and a maximum of 1370, and a median and a mean, which are close to one another, but not the same. Let's look at a histogram. There's a histogram. Again, I'd like to make sure everybody can see that histogram, because as several people commented in comments last week, R is a very visual environment. So, and I am a very visual scientist, so I like to have things visual. So everybody can see that. Oh, somebody said CTL and make it bigger. So what should I make bigger? I don't know how to make the help files bigger, but is this visible to people? Because if it's not, we're going to need to do something. Is the histogram? Can people see the histogram?
I can see it. Others. Okay.
Is it easy to read the X and the Y axis?
Yeah, from my end. But I think you could also make it a little bit bigger if it's possible.
I think there is a way. Let's see if we can do this. PARCEX equals 1.3. And then I'm going to do the histogram again. That makes the text bigger, which is important. I mean, the graphic itself should be. So what I've done is I've used this character expansion parameter, and I've expanded things by 30%. If I go to CEX equals 2, and then do the histogram. Maybe I should do that.
I think the previous the CEX 1.3 was better, if I'm not mistaken, because there was equal proportion between the plot and the text.
Yeah, that's true. I mean, obviously, if you're looking at something, if you're putting something into a paper you're writing or a presentation, then you can get away with a lot of this. All right, now let's look at a plot of the data. Okay, so that is a plot of the Nile data. I haven't told you what it is, by the way. But the reason okay, so there's a plot of the Nile data. It's a time series. So when time series data are plotted, by definition, I mean, by default, they are plotted as a line. I'm not sure I agree with that. It's not the simplest default, but it is what R uses for plotting. So again, let's make that plot a little bigger. Let's make the lines a little bigger. So I'll type line width equal to 3. And I'll hit Control Enter. You can see the lines are bigger. Now, what are we looking at here? Well, we're looking at a time series of data, and it's called Nile. The reason I had you download the data from my website was that I wanted to make sure that people could download data from the internet. But it actually is the case that this data set, and I'm going to go back to the console window and type in capital NILE. I get a help screen that says that the object capital NILE is the flow of the river Nile from 1871 to 1970 in 10 to the 8th cubic meters per year, presumably. So what you can actually do is, without access to the internet, have access to the Nile capital NILE data set, because it's part of the data sets that are loaded with R. Let me see if I can make that bigger. Tools, global options, appearance, and then does it give you access to the, I don't want the editor font. I want the, well, I don't know. I'll make a note to myself to see how I can increase the help screen text. So the other thing about the help screens, and I mentioned this last week, is that you have a whole bunch of examples that you can run to learn more about the Nile dataset, or any other command or any other object that's loaded in R. So this Nile object is part of the datasets loaded with R, but I've created an object. I've recreated it by loading in the data up on the top of the screen. And again, remember that I'm typing in, I've created on this upper left window, I've created a script that is, I can save. So I can go File, Save, and I'm going to save it on my desktop as Nile _analysis.R. So now I have a program on my desktop, and this script that I've typed in, all of the commands I've typed in so far are going to be on that in that script that has been saved on my desktop, which I can edit. Somebody suggested in a chat that I use 1.5. Let's just try 1.5. And then I'm going to plot the data again, but I'm going to plot it this time with points and lines. So type equals, I'm going to overlay points and lines. So I've set the character expansion to 1.5. I've given it a line width of 3. I'll make it even 4. Let's, can't hurt to try. And then I'll hit return. 4 is a little big. It also expanded the point size. So let's just, no, that's all right. So let's deal with that. I like that. That's okay. So let's make that nice and big. So we are looking at, I guess I can, if I maximize that. Okay, let's just, I cannot emphasize enough how important it is to visualize data. So what we're looking at, so let me get some comments from people on what they're seeing. Let's put a title up there also. I'm going to type it in again. I'll put in a title. I'll just add a title. I'll take it from the help file. Annual flow of Nile. Annual flow of Nile. Tape it right from the title. I just typed in the command title. Got that. So let's talk about what we see there. Let me hear some comments on what they see. Either problems with what they see or observations of what they see. Something they don't like, something they do like, something they see is happening. What's the matter with the x-axis? What's the matter with the y-axis?
Unit.
If you saw this in a paper, what would you say to yourself?
We don't understand. We don't have unit on the graph.
You don't understand what? Why don't you type your comments so that I can see them if you can? I guess if you're on a phone, it's a little awkward. All right, yeah, we don't know what the units are on the y-axis. That's one good thing. So we got to fix that. Let's make a note to fix the y-axis. What else? Anything you can conclude from what you see there in terms of the behavior of the flow of the Nile?
I think the time, I guess the time flow.
Yeah.
It's from 1871 to 1970, and the time series is not really, I think, reflecting that. I don't know.
Right. So we have the two axes are not labeled correctly. I did not introduce the axes or the units into the data set. And someone said that it looked random, or it does seem like it's reducing over time. All right, so those comments are very interesting. The comments are aesthetic, which is I don't know what I'm looking at. I know I'm looking at a time series because it's labeled as time. I don't know what the units are. Are they years? Are they decades? Are they minutes? Are they seconds? I don't know what the units of the y-axis are. I don't know what the volume is being measured in. So I'm going to reduce that graphic and start cleaning up the time series. So actually what I'm going to do is I'm going to recreate the time series. I'm going to go back up to my command here. And instead of calling it TS equals Nile, the first column of the data set, I'm going to say start. And all I need to do is tell it when it's starting. So it's 1871. Right? And then I type in Control Enter. And now if I type the same object again, if I type plot, I go back to line 18 in my script and I execute that command, it plots it with years. So all I needed to do was say to R, the time series starts in 1871, and then it says, okay, I know that it's 1871 to 1970, because that's 100 years. As far as the y-axis is concerned, we don't have a way of storing that information in the time series object, but I can plot I'm gonna clean up my plot now. This is one of the reasons why typing with scripts is so useful. I'm going to type X label equals, and then again I'm going to use 10 to the, I know from the help file, I'll go back to the help file, and it says 10 to the 8th meters cubed. So 10 8 meters cubed. Gotta make sure I put quotes around that string. And I'm getting an error. Okay. And then if I, let's see, anything else? Let's make those points PCH equals 16, because those, let's make those dots now instead of circles. Oh, I'm sorry. I didn't mean, you see how you're not thinking, so I'm going to make that the Y label. Okay, 10 to the 8th meters cubed. I don't really like that unit. What is 10 to the 8th meters cubed? I mean, that's a 1 followed by, I mean, what is 10 to the 8th? 108, 1E8, the same thing. It's 1 followed by 1, 2, 3, 4, 5, 6, 7, 8. I mean, I don't even know what that is. I mean, that's 100 million cubic meters. Well, that's 100 million cubic meters is a tenth of a billion cubic meters. So what I'm going to do is I'm going to go back to my creation of the object the first time, and I'm going to divide it by 100. And now I'm going to plot it. And this is not going to be a 10 to the 9th cubic meters. Well, 10 to the 9th is a billion. So I've divided it by 100 so that I now have, I know that I'm talking about billions instead of hundreds of millions. I know that sounds a little contradictory. And then I plot it again, and I'm going to give it, okay, billion cubic meter. I'm not even going to use, I'm not going to be fancy. I'm going to say cubic. And I'm going to add I can actually add the title right into the plot. I'm going to stop here a second to give people time to move that up there. Okay, so now I have a plot that I regard as being reasonably. Actually, what I'm going to do one more thing. I'm going to add a y limits. I'm going to have it plot between 0 and 15. And then I'm going to stop. Now I can see in my plot that given that we're dealing with an actual volume, which can range from 0 to infinity, I can see the plot of the River Nile over 100 years. I can compare those values to 0, which is dry, which is no flow at all, which has never happened. And I can discuss what I'm seeing. So let's hear some comments over about what people are seeing, either aesthetically or, more importantly, analytically. What do you see going on there? Any comments, questions?
Dropping in with a question. For the annual flow, is it the maximum flow we're looking at per year? Is it the maximum flow per year we're looking at, or?
I don't really know. I think that I know the help file is kind of small, but I think what you should probably do is one of the things about the help file is that they're frequently references. And so here are references to 2 articles from 1978 and 1993. So you could go to those references and look them up. That's a good question. What I think is, based on my limited knowledge of hydrology, is that it's actually the flow. So that if, for example, if you go back to, let's look at Nile.ts1, that's the first observation. What happened was that during, or let's just head Nile. It doesn't, why doesn't, okay. So what that data set is reporting is that in 1871, 11 billion cubic meters of water were flowing through over the Nile riverbed at Aswan, upstream from Cairo. So what we're looking at is not the maximum flow, but the total flow from January 1871 to December 1871. That's all the water that flowed through the Nile River in that period. It's not a maximum flow, it's the total flow. That's a good, I think that's a good, but that's a good, because if it said something like feet per cubic meters per second, then we'd know that we'd have to be talking about a maximum or a minimum. That's a good question. So somebody said it's almost like I'm seeing the water level over time. Yeah, that's exactly. I mean, it's not the level of the river. I mean, again, I'm not a hydrologist. It's not the level of the river, but it's the amount of water flowing. If you think about the river as a pipe, then say what was approximately what was the minimum flow during that period? I mean, somebody can type in min. Let's just do range. So but without typing that command, or if somebody types it, they can give me the answer. But if you're just looking at the plot, what does it look like the minimum flow was? Actually, I'm gonna do this 5. Yeah, looks like the minimum was about 5. What I can do, and I did this last time, AB line. I'm gonna type horizontal equals, and I'm gonna have R. Let's use a line type 3. I'm going to have R and a color equal to gray. I'm going to have R plot for me a line across the plot with the range at the minimum and the maximum. Gray was not such a great color. Let's use red. And let's use a bigger line width because I want LWD equals 2. Okay, so I had R plot for me 2 horizontal lines, one through the minimum and one through the maximum. I don't even know what those values are. I mean, I don't know what they are exactly, but I can quite easily see from the plot that the minimum is around 4 or 5, maybe say 5.5, and the maximum is around 13. And if I do a summary of Nile.ts, I can look at not only the minimum, the maximum, but the quartiles. Minimum 4.5, maximum 13.7. Now, I don't want to get away from our script here, so I'm going to go back to the script and type, and that nice little command that I typed in the command window, I'm going to put that on my script. There's my script. So now when I run the script, I'm running out of space here. I'm going to make this R window a little bigger. I don't know. I should have my wife log in in her computer next door. So I'm going to type it. So there I typed in the command that is in my script. And then I've typed in the AB line. And I'm going to make that a little, bring that up so we can see it in the command window. There are my maximum and minimum lines. So there's quite a bit of open space, white space on that plot at the bottom, but I'm okay with that because it enables people to see that the range was, say the minimum, you can see from the plot itself that the minimum was maybe 1/3 of the maximum. And you couldn't easily do that by, if the plot were shown on its range rather than the data. Okay, well, we're not, we don't have a lot of time here. Okay, let's plot the data. I'm trying to see how much what I want to skip. Let's do a histogram. Let's do a histogram because that's all right. So I'm going to do hist file.ts. So we didn't talk much about this last time because we were doing a simulation, but here we're going to try to analyze the data. Well, we've already done some analysis. We know what the minimum and the maximum is. But obviously, if we're looking at time series, we're looking at a phenomenon that's occurring over time. So we're interested in how it changes from 1 second to the next, from 1 minute to the next, from 1 day to the next, from 1 century to the next. And here is the challenge. We're looking in this histogram. The challenge is to understand or explain or predict or forecast these numbers. So we have a phenomenon that's ranging from 4 to 14. So it's ranging by a factor of over 3 over the time. And obviously, if you were an Egyptian hydrologist or a farmer, you'd be very concerned about understanding the behavior of that time series. And that's the goal. What our goal is to essentially reduce that histogram, reduce the width of that histogram by creating a model that explains some of that variation. That's the variation we're looking at. All right. Again, if I put in my summary, AB line B equals summary file.ts. Make this bigger. For ty equals 2. Right? That's the variation in my data. Mean, minimum. I want to understand why that value changes so much from year to year. Go back to my prior plot. That's the variation I'm trying to understand. If I can understand why those dots bump around the way they do, then I could predict what's going to happen in the future, understand how I might want to change that flow if I wanted to change it somehow, predict why it's changing. So that's my goal today, at least, is to understand and predict, and sometimes forecasting is the word, but I don't really like the word forecasting because it's ambiguous. So one of the things I might want to do is see if I can filter that data so that it perhaps looks, I can perhaps look at some trends within it. And so one of the things I do up in the command console is I type in filter, a question mark filter, the letter, not filter, and I get a help screen on filter. I'm going to make a note to myself how to make the help screen larger. So if you're running R on your computer, help larger. If you're running R on your computer, you can see that help screen, and it's a filter that takes away some of the noise. So what I'm going to do is I'm going to add a filter to that data, and I'm going to give it a width of a decade. So actually, the other thing I should do is put in a command here. a comment. I'm going to reduce the size of the, I'm not really interested in the environment. And so I put a comment there so that I know, and I'm actually going to put another space there. So I've moved from the analysis, I've got the title of my script up here, and then I've got plot here, so I know what I'm doing. Somebody just had an accident outside my door. I heard this crash of the screech of brakes and the collision of two cars outside my window. But I don't think anybody was hurt. It didn't. It sounded serious though. Probably you'll hear sirens in the background in another few minutes. So we're going to run a filter, and the width of that filter is going to be, go back to my, so what I want to do is look at a filter. I want to filter out some of that noise. My first step is to look at a filter. And I'm going to give that filter a width of 10. So I'm going to create a variable. I'm going to set it to 10. Enter. So I got width. If I type in width again over in the console window, at 10. And I'm going to create a filter called F. I'm going to be called filter. It's to be done on nile.ts. And it's going to be, filter is actually going to be a string of ones. I'm going to repeat the number 1 10 times. Then I'm going to divide that string or that vector by 10. And I think I'm done. What did I do here? Let's take that out and show you what it is. Well, let's go over here. All right, so my filter was REP 10, 1, 10 times. So if I, in other words, if I repeat the number 1 10 times, I get a string of ones. If I divide that number by 10, I get a string of tenths. And the sum of that filter, width, I repeat, sum of that filter is 1. So it's a filter that passes over those numbers 1 by 1 by 1, multiplies each one by a tenth, sums them, and divides by 10. So it's a filter that filters out the data by decades. It's sometimes called a rolling mean, sometimes called a rolling mean, sometimes called a, I'm blanking on the other term for it, sometimes called a moving average. It's basically a moving average. I'm going to put that in to remind myself. But R calls it filter. The other thing I'm going to do down here, I'm going to put in the command E and B just to remind myself that the end of my script is there. So that's my filter, F. I'll just, oh, so what I've done is I've run the filter on I haven't run it, I guess, have I? No. Control F, Control Enter, and I run it, and then it shows me that I've got another time series. Here's the value of my time series. The environment tells me that by creating a filter, by running this filter F, I've got another time series, which ranges from 1871 to 1970. But it is now, it has filtered the data with a moving average, and I can plot that as a This is a time series. And there it is. There's my filter. Now, that's a good way to visualize the filter as a start. But what I really like to do is to see the filter over the data. I'm going to go back to my plot up here. And then I'm going to add the filter as a set of lines. I'm going to color it blue. I'm going to give it a line width LW of B. I'm going to overlay it on top of that plot. I don't know whether blue is such a great choice. Maybe let's use, how does orange look? There's a filter laid over on top of the data. So looking at the filter by itself it tells us very clearly what the behavior of the filter is, but we're more interested in looking at the filter overlaid on the data, at least at this stage. So if you've not heard of, probably everybody's heard of a moving average, but this is an example of, it's a filter in the sense that it filters out a lot of the noise. So looking at the filter, can anybody give me some ideas about what's going on? What does the filter tell us that the data perhaps didn't? I'm looking at the chat window. If somebody joining, he's only going to be around for 10 minutes. So I'm looking at the chat window. I'm waiting for somebody. If I hope so people can see the filter. I don't know whether red would be better than. Red's always a good color. So someone said that they observe a, let's add a line there. Somebody said they observed a decrease at, I would say, they say they observed a decrease of flow after 1920. It looks to me as though the drop, if we go back to our previous plot, it looks as though the drop was around 18, this is 1880, 1890. It looks like the drop was around 1890. So that was a good observation, but it clearly shows that the filter clearly shows a drop at around the late 1890s. I mean, this is 1880, this is 1890. So that's, and you can see that in the plot itself. You can see this drop around 18, this is 1880, 1890. But I can look at each of the years. Look, let's do this axis, just to make sure I can see each of the years. Axis, 1, I'm going to put the axes at SE 18, 10 times 1870, 187, 97. So what I just did was I put axes. I'm just kind of lazy. I don't know. I should, let's not be fancy. Let's just 1870 to 1970. So I just added axes at every decade. I added axes at every. It's I'm sorry, CQ 1870 to 1970, steps of 10. I gotta go clean up my act again. So I'll do the plot again. I go up to the plot and I just hit return the plot. I hit Control Enter. Control Enter. And then I put in my lines. I'm not going to put the lines in. I put my filter in. And then I put in change the axes to be every 20 years, and I change them to be every 10 years. Okay. After the fact. So I can see that that drop was indeed at 1890. And if you go back to the help file, you'll see that there's some discussion as to what happened in around 1895 or 1899 or something like that. So we've got we've already learned from our filter that there is something that the behavior of this time series is can be understood, or at least to some extent understood better by filtering the data, filtering out the yearly data. Another thing we can do is a regression. See, probably regression would have been the first thing we do rather than the filter, but you know, regression is a little more sophisticated a tool, so we're not going to. And what I'm going to do is I'm going to, if I look at the time from the data, it is a time series. I hit return, and it shows me up in my console window that the time is itself a time series. Because after all, I mean, you think about it kind of metaphysically, the year is a label we give to a period of time, 365 and a quarter days or 12 months or however many seconds you want. So I can regress the data. I mean, first I type, what is a linear model? I mean, I'm going to give you the terminal, so I'm giving you comments, so it's not going to cause any problems. Oops, and there's the help file for linear model. So I'm going to run a linear model, LM, Nile, yes, and I'm going to regress it on the time from the data set. I type in return. I can see in my console window, I have a regression model that says that the flow of the River Nile. Oh, can I explain moving average? Somebody asked a question of, can I explain moving average? Not in 5 minutes, but again, I would suggest that you run R. Also, you know, the other thing is just go to your browser and type in moving average, type in filter. But basically what it does is it takes for every 10-year window, it takes the values and adds them up and divides by 10. Then it goes to the next 10 years and adds them up and divides by 10. So it moves year by year by year, taking the years. I mean, we could spend a whole lecture on the subject of moving average, but I would suggest that you go to Google or DuckDuckGo. DuckDuckGo is my favorite web searcher, and type in moving average. Also, Excel has a moving average. It has a moving average routine. All right, so I've typed in, I've run a linear model, and my linear model says that in order to predict a straight line through the data, I get an intercept of 61 and a y a coefficient of minus 0.027. And I'm going to actually, easiest thing to do, the best thing to do is to put that into an object. So I'm going to run it again, but this time the result is not going to give me it's not going to give me any output. It's just going to run that object into fit. And if I type in fit, I get the results. Same thing. But if I type in summary, I can summarize that. Fit. I get a longer description of what it is. It tells me, and this is where the important things, information is. So it tells me, this is my command that I typed in on the script. Summary fit, it says that here's the formula that I used. It predicts nile.ts from the time in the data. It gives me my residuals. And I can compare those residuals to the summary, Nile, my residual, the value of Nile.ts ranged from about 4.5 to 13.5, which is 9, and my residuals range from about -5 to +4. So my prediction is not, it doesn't do a great job of predicting the data. The R squared is only about 0.2. Nevertheless, the estimate of the regression coefficient is statistically significant, which is an interesting situation. So we have a prediction model that works, but is not doesn't do a great job of predicting. Let's go back to my plot. Let's just put in the plot without the actually let's do this. Let's put the plot in for those of you who are having trouble moving around. Yes. And let's do type equals just a point. And let's not worry about the axes. Oh, let's just do with PCH equals 16. So there's my data again on a different axis. And let's add in a regression line, or the regression line. There's my regression line. And we're almost about out of time. If we're going to keep ourselves to the hour, we need to think about stopping. So let's give me some comments about that regression line. What does it show?
I think the yeah, sort of high residuals, although it fits properly to the data, but there's still high R squared. I think it has a low R squared. Sorry, that's a low residual, a high residual, a low high errors. I think.
And what is the nature
Okay,
of the slope of that line?
it's negative, negatively correlated.
Yeah, it suggests that over the period of 100 years, there has been a negative trend to the data, although it's not been very strong. It's significant, it's statistically significant, but it's not very strong. Okay. In fact, that it and in fact, if you look at the coefficient, to fit EFF. That's how we can look at the coefficients themselves. So if you look at that second coefficient, minus 0.27, and you multiply it by the length, Nile.ts, what I've done is the coefficient says that the regression line predicts a decline of minus 0.02 billion cubic meters per year. If we multiply that yearly change by the number of years, we get the predicted decreased flow during that period. So during that period of time, the model predicted that the Nile River had decreased by 2.7 billion cubic meters over the whole period. So we multiplied the regression coefficient by the number of years. I mean, the regression coefficient is the change per year. We multiply it by the 100 years. So obviously, if we wanted to be silly, we could say, what's it going to happen in 200 years? Well, we multiply by 200. It's not silly, but it's a little, it's sophisticated. It's a sophisticated idea, but it's kind of silly. So we'd say, well, okay, over the next 100 years, if that kept going, by 2071, the Nile would have decreased by minus 5.4 billion cubic meters. Obviously, that's a silly idea, but if I wanted to plot it, I could do that. In fact, I could go plot Nile.ts xlim equals c, right? 1870, 2070. And let's give it y lim c 0. Running out of space here. Here's my data. Now I fit the line to it. So that's a sophisticated thing to do, but it's silly because who knows what's going to happen in the next 100 years. But that's what the regression line says. The regression line says that by 2071, the flow of the Nile would have gone down to 5 billion cubic meters. Okay, well, we're 4 minutes past 1100 Eastern Daylight Time. Let's do that. Any questions? All right, so let's, if we, one more hour or we'll do a half an hour. So we're going to stop at my time, 11:30, which is 25 minutes from now, about 24 minutes from now. So given that we've got some more time, let me get some questions. Problems, issues. I really like to hear from people. Oh, okay. I'm sorry. I should be looking. We can adjourn 1 more and a half. I have a question about linear regression on non-continuous data. I'm not sure what's meant by non-continuous data. I mean, you can run regressions as long as you have 2 sets of data, an X variable and a Y variable, you can run a regression. In fact, you can run a regression as long as you need a dependent variable and as many independent variables as you want. Or if you're running, principal component analysis. I mean, the whole question of linear models is, that's a whole, that's years of study. I mean, I took at MIT, I took 2 years of econometrics, of which, so you can run you can run regression on ordinal data, on continuous data, it has to be quantifiable in some way. It has to be either turned into factors or something like that. But that's a good question. I mean, it's a very robust technique that can be used to do all kinds of things. Any other questions? I mean, I know there are other questions. Anybody have any problems with running R, looking at RStudio, seeing my screen, whatever? I'm going to make my my screen smaller so I can see. All right, I'm going to keep my eye on the chat window. Let's do a couple of things. Let's look at this regression model. It's obviously it's good and bad. It's good in the sense that there's a statistically significant slope. It's bad in the sense that the R squared is not that great. Let's compare the residuals of the model to the data itself. So let's do PAR MFROW equals C2 1. And then let's do a histogram. There's a histogram of the data, and let's compare it to the residuals. So I'm going to type in. Let's look at what the residuals look like first of all. There they are. So the residuals from that model are a list of numbers, 100 numbers. They're the residuals. They're the difference between the actual values and the regression line. And let's look at a histogram of them. And let's make sure that we use the same for and 14. What am I doing? Fit, fit, resid, hist, what? Error, unexplained symbol. Xlim, hist, why am I? It's not showing an error message. Hist, fit, question mark, residual. What did I do? Oh, residuals. Residuals have to be between we need, okay, minus, let's see that. The difference between 4 and 14 is 10, so let's do minus 5. And minus 5 and 5. Now I'm going to show the same thing again. Wait, hit my, right? So there are my residuals. They're both, and there's the histogram of the data and the residuals. They're both on the same scale. As you can look at, you can see those. Let's maybe do CEX equals 1.3. Okay, so you can see my plots are on the two residuals are shown on the same scale. In other words, the first histogram shows this range from 4 to 14, which is a range of 10, and the residuals are on a scale of -4. I wanted -5 to +5. How come it didn't do -5 to +5? I have approximately the same scale. You can see that the units, these are units of 2 from 8 to, each bar is 1 unit, and it's the same on both scales. And you can see that the histogram of the residuals, which we'd like to be really small, is not that much different from the range of the histogram itself. All right, so let's do one more thing with the Nile data. Let's do a forecast. And this you may, what you have to do in order to run forecast is to add the library for the forecast library, and you probably don't have it. So I perhaps should have. If I hit return, okay. So there is a forecast library, and I can. So what I suggest you do is you load the forecast library. In order to do that, you have to go up to my I should know what. I don't do this much with. It's not file. Where is it? I gotta go. All right, I'll make a note to myself to learn how to run. I usually run R GUI libraries in RStudio. I don't know how to load them in. So there's a forecast library, and I'm gonna. So you probably, I'm getting ahead of you guys because you haven't loaded that library, and I can run a forecast on TS, and I get a result. So what it does is it says, okay, you want a forecast, and there's a technique for running forecasts. So if I do question mark forecast, get a help screen. It's a generic, there's a whole bunch of help files. There's not too much in the way of examples, but it's a means of doing a forecast. And I'm going to run it on the Nile data simply because it shows us that forecasting is not very useful here. Make a plot of that forecast. Let's go back to so that's a forecast of, oh, I can actually make it a free, you probably can't see that, so I should not do that. I should just make it maximum. And let's make the lines bigger. 3. Okay, so what forecast has done is generated a forecast into the future. Go back to the console. It's generated a forecast of the Nile flow from 1971 to 1980, and it's given us a port forecast. In other words, it's given us a specific scalar, a prediction for the future. And you can see that every one of those forecasts is the same number. So it's saying is that the forecast model, which is based on econometric time series of, let's see, ETS, exponential smoothing. It's exponential smoothing. So the forecast, which is based on the behavior of the data over the past 100 years, says that every year will be the same, but that the standard deviation of those predictions will increase from, or the 95 percentile prediction will go from 5.8 down to 5.6. That's the bottom, and the top value will go from 10.9 up to 11.2. So the standard deviation of those forecasts increase as you look out in future. And of course, obviously, we're just touching the surface of a whole bunch of complexities. All right, so what I want to do in the last 10 minutes, I mean, I've skipped, let's see, did I do everything I wanted to do? Residuals, I think the other thing I wanted just to point out to you is that you can plot the data in lots of different, well, I don't need to do that. All right, so let's save that script. Sorry, cancel. I'm going to go back to the script window and I click File, Save, choose encoding. Why is it asking me to choose? I'll take UTF-8, I guess. All right, so if I exit the window, I can open up that file, and there's the script again. So I've saved the file on my desktop. You can't see my desktop, but you can get an idea if I can open up the file, I can save it, and so forth. So let's close that file, and let me just use the console window to explore some other ideas just in the next few minutes. Takes us to, all right, so if I type question mark, I can also type help. I think you can also do data sets. Data sets. Oh. I should know how to do this, but I don't. So there is a data set called L deaths. If you go to, if you type in help L deaths or you type in question mark L deaths, you get a help screen that tells us monthly lung deaths from lung diseases in the UK. So just to let you know that that R can handle other kinds of data time series besides months. And if I type L deaths, get an interesting matrix. So the matrix shows me the number of I'll just type this in, monthly deaths from bronchitis in the UK. Put it in as a command. As you can see it. Monthly deaths from bronchitis, emphysema, and asthma in the UK, 1974. So it's an interesting data set because if you look at STR, tells us it's a time series from 1974 to 1980, but there's 72 values in there, 72 being 12 times 6. We have 6 years of data, but the data is organized into months. So essentially we have monthly data, but grouped by year. And if we plot the data, we can see why that happens. And again, I'm going to use, I like to use by limb. Let's see, 0. Let's just, no, let's not make it 0. Well, let's do 0. 4,000 for grins. Ah, works. Okay. So now we have a different kind of time series, more complicated, more structured. So I look at its attributes. It says it's a time series from 1974.00 to 1979.917, and it has a frequency of 12. Why, what is 1974? What is 1979.917? Well, 0.917 is the 11th month of the year. So it divides the year up into 12 equal spaces. Each one the value of 12, 1/12. It's a very intuitive way of organizing the year. I mean, you can also organize, and it could also, so, I mean, it's not exact because we know that February has 3 fewer days than January. Is that 131 versus 27, 27, 20, 29. So it's not exact, but it's good enough for the analysis. So I'm going to ask questions. What do people see going on there?
So, Dr. Lee, please, can you expand the window? Sorry, Lee. The visual
plot window.
The plot window, yes. All right.
Yep, we can. Can you see it? Oh,
I
you
can't. I can see
can't
the labels.
probably
Yeah.
probably can't see the. I'm gonna make the PARCEX equals 1.5 and plot it again.
Okay, this is good. You can just expand the window. Yeah.
So let's hear some comments about seasonality. What is seasonality? Okay, seasonality. Deaths peak at a similar time every year. It's clearly a seasonal pattern to those deaths. And if we wanted to help understand what's going on, maybe we could plot an A-B line at H equals 19, no, V, sorry, V equals 1971 time. No, I don't think I want time. Let's just do 1971 to 1974, 1979, 80. Okay. And I'll maximize the window again. So what I've done is I've put lines through, I've made vertical lines at the beginning of each year. So where are the peaks in those data? Nineteen 75.0 is the beginning of the year. 1976.0 is the beginning of the year. So I've put lines at the beginning of each year. Convention in the Christian calendar, so-called, is that the beginning of the year is in January. So in the northern hemisphere, that the year starts out at well, anybody who uses the I guess it's called the Gregorian calendar or the Julian calendar, the year starts in January. So where are those peaks? What is the winter? Yes. And if you go back to the help file, which again, I don't know how to make it bigger. The peak, the major peak was around February 1977. Looks like January, February, March. If I go back to the help file, monthly deaths from, why did I want to go back to the help file? These are, all right, so these are deaths from, oh, and I also have it on my label. All right, I didn't put it on my label. How come I didn't? Oh, I didn't show the label. But if you go back to the help file, you can see that the deaths are from bronchitis, emphysema, and asthma. They're lung deaths. And so that the reason why this data set is so useful to look at is that the world is now experiencing deaths, many deaths from a lung disease or a disease that interferes with the lung. And so the LDeath data set from R is a highly appropriate one. We only have less than about a season's worth of data in the world to look at what the seasonality of it is. But the lung death data set from R is a very useful one to use. And the other thing is that you can, and I don't think I'm using, all right, so I'm going to go back to the console window. I can also aggregate data. You see right there that RStudio is giving me an option of aggregating a time series. If I do aggregate, it knows that I want to aggregate those data by year. And so what it's done is it's gone through that matrix. If you look at it, a matrix, what it's done is it's aggregated each of those rows and give me a total. So if I were to look at the total here for the first 1974, that number, if I sum across that matrix, that number is this value shown here, 26,000. So R is very powerful, has some very powerful tools for analyzing time series. And if I wanted to look at the trend of those data over the period, I could plot that. I wanted to look at it. Originally, I was just looking at, monthly data. Just right, plot. Let's do this. Plot. The last thing I'm going to do. I'm going to do a P par MF row equals. Oh, let's just plot the data and then add the plot L deaths. Getting sloppy. EATH L deaths. I'll do D equals 3. And then let's plot over those lines. Aggregate L deaths. And let's do that as a I'm going to plot over that the aggregate data. Oh, and obviously it won't plot there because it's summing, so I'm going to divide them by 12. And they're the aggregate deaths plotted over the monthly deaths. Okay, that's enough for today. So it's I'm on overtime now. So I want to thank you all. Stephen, did you have any closing comments?